Hello Science 30s. In this video we're going to be learning about gamma radiation and gamma particles and what that radiation looks like. So you already know a bit about gamma radiation, gamma waves, as you've learned in with EMR in our last week. And we know that gamma waves are high energy, and high energy radiation. And in this case, guys, it is not, there are no protons, there's no electrons involved with gamma radiation. It is simply photons. And that means it has no mass and no charge. And so we'll take a look at how that looks. Now, once again, if we go to our table here and we look up what a gamma radiation particle looks like, or a gamma particle looks like, here it is right there. So you see that 0, 0, and then the symbol there, gamma. So right there, and our kind of like a little Y, if you will. Okay, and that's our gamma particle. So again, we're going to jump right into a question here. There's not much more to say about gamma radiation, so we'll just get right into a question. So cobalt-60 is a source of gamma radiation that is frequently used to treat patients with cancer. Machines used in modern cancer therapy, like the one in the photograph, can focus narrow beams of gamma radiation from over 200 cobalt-60 sources to destroy cancer cells deep within the patient. Write a balanced nuclear equation to describe the emission of beta and gamma radiation from a cobalt-60 source. So it is important to realize here, guys, that there are two different radiations happening. There is beta and there's gamma. If it was just gamma radiation, guys, that there wouldn't be much to put. We would just put a gamma wave and that's it, or gamma particle and that's it. Because of the addition of the beta in this case, we do have to do some mathematical work here in this question. So anyways, we'll get right into it. So the way I think, again, we should start this is start with our nuclear equation, what we know and what we don't know. So we know that cobalt-60, I believe that's element number 27, is going to decay. Now that's going to decay into a beta particle. Sorry, that's a gamma particle plus a beta particle, which is an electron, plus, and again, in this all this information, they don't tell us what the unknown is. So this is going to be A, Z, and then X. All right, so once again, we have our top numbers which are connected. So 60 is going to equal 0 plus 0 plus A. And we are going to have 27, which is equal to 0 plus negative 1 plus Z. So we go ahead and now we find out that obviously A is equal to 60 and Z is going to equal to 27 minus negative 1, which is going to equal 28. Okay, so now we can put this all together. Now, first of all, now that we figured out this 28 here, that we know now, we can figure out the element that this is decaying into, and that's going to be nickel. So that's going to decay into nickel, and now we can put this together. So we're going to say 60, 27 cobalt. So cobalt-60 is going to decay and make a gamma particle plus a beta particle plus, and now we're going to have still the 60 up here. We're going to now have 28 down here, and this is nickel, and there is our final nuclear equation for this gamma radiation and beta radiation.